Graphs of functions. The graph of a function gives us a way to visualize a function. So if f is a function with domain A, then the graph of f is the set of ordered pairs x, f of x, where x belongs to the domain A, and these points are plotted in a coordinate plane, which is a fancy way of saying an x-axis and a y-axis. In other words, the graph of f is the set of all points x and y such that y is equal to f of x. That is, the graph of f is the graph of the equation y equals f of x. So for example, if when we plug in x equals 1, we get this point, and when we plug in x equals 2, we get this point, etc., you can draw a curve that passes through the points that satisfy the equation. A couple of special types of functions that have very simple graphs are constant functions and linear functions. So a constant function is when y is simply equal to a number or a constant. For example, y equals 3 is a horizontal line passing through 3 on the y-axis. The function y equals 2x plus 1 is a linear function, right? We know that this is the equation of a line with a y-intercept of 1 and a slope equal to 2. And so we get this graph. Now, technically, both of these are linear functions, but it is kind of nice to separate constant functions from other linear functions because constant functions do behave a little bit differently than linear functions. We can also graph functions by plotting points. So for example, if I want to graph the functions f of x equals x squared, g of x equals x cubed, and h of x equals the square root of x, these are not constant functions nor linear functions. So when we first graph these kinds of functions, we typically will be plugging in values for x and observing the function values and then graphing those points. Now, for the function x squared, notice that they put plus or minus 1/2. That's because when you plug in positive 1/2 or when you plug in negative 1/2 and you square it, you get the same thing. You get positive 1/4. And they do that for these points. And you can see that when you plot these on an XY coordinate system, we get this very familiar shape that we call a parabola. X cubed is a little bit different. The reason it's different is because when you cube a negative number, such as -2, it stays negative, right? So if you plug these numbers into the function x cubed, you observe these values, and when you plot those, you get this function here. And finally, the square root function. Remember, we're not allowed to take the square root of a negative number, at least not when we're talking about functions. So the only numbers you can plug in for x here are going to be positive numbers and also 0. And when you plug these numbers in, you observe the following values. And then if you plot those, you will see that you get this graph here. Now, just for clarity here, when you plug in a number like 2, you get the square root of 2. You might need to use a calculator to approximate that the square root of 2 is 1.4. And that is why that point ends up right here, because 1.4 is about right there on the y-axis. So sometimes you will need to, have a calculator handy to be able to approximate some of the values so that you can get a decent graph. We can also graph functions with a graphing calculator or with software on a computer or a phone or an iPad. For example, if you're asked to graph f of x equals x cubed minus 8x squared, there is a way to do this without using a calculator, and we will be talking about some of those methods in this class, and also you will talk about it in calculus. However, if we just want to graph this quickly, we can use software to do it for us. But you still have to be careful, because if you just plug this function into a graphing calculator and you don't think about what values of x you're looking at, you might get pieces of the graph, which doesn't really tell you the whole picture, right? So you might need to change your viewing rectangle. In other words, you might need to change the X values that you're looking at and also the Y values that you're looking at. So for example, over here, you can see we have Y values from negative 100 to positive 100. And we have X values from negative 4 all the way to positive 10. And this same function, when viewed in this rectangle, gives you a much better picture of what's going on. So even if you're using a graphing calculator, you still have to know some things about graphing the function in order to be able to see a good picture. Next, we have the power function. The power function refers to the function f of x equals x to the n power. So what we want to do here is take a look at the power function for n equals 2, n equals 4, and n equals 6. So in other words, we're graphing x squared, x to the 4th, and x to the 6th. And we'll do that in the viewing rectangle from x equals negative 2 to positive 2, and from y equals negative 1 to positive 3. Now, if you do this, you'll notice that the red graph here is the graph of y equals x squared. And then if you did y equals x to the 4th, you would notice that the graph would change a little bit. So notice that it kind of looks like a parabola, but it's not a parabola. And when you look at x to the 6th power, that's this blue graph right here. And again, it looks very similar to x to the 4th power. So this is what even powers look like. And so you could imagine if I were to ask you to graph x to the 8th power, it would look a lot like this blue graph. In fact, it would probably come in something like this, right? And then it would take off in this direction. And that's not a very good picture, but I think you get the idea. Now for odd functions, so odd power functions, f of x equals x to the n for n equals 1, 3, 5, etc. So x to the 1, of course, is just x. So this is the graph of y equals x. X cubed, we just graphed a minute ago. It looks something like this. And then if you were to plug in numbers and get values for x to the 5th power, you would get this purple graph right here. And I want you to notice that x to the 5th power and x to the 3rd power look very similar to each other. And so if I was to ask you to graph x to the 7th power, you would expect to get a similar type of graph. Now, what conclusions can you draw from these graphs? Well, there's two really obvious things about these graphs. The even powers go up on both sides, don't they? Notice that there are no negative numbers for the even powers. That's because when you raise a negative number to an even power, you always get a positive number. However, on the other set of graphs for the odd powers, you'll see that the graph is going up on the right side and it's going down on the left side. And this is because when you plug in a negative number for x and you raise that to an odd power, you get a negative number, right? So the shapes of these graphs over here and right here, they're very similar to each other, right? Notice that. Just take a second here to look at, the blue graph here, right, which is x to the 6th, and the purple graph over here, x to the 5th. The behavior right here for x to the 5th and here for x to the 6th is very similar. So the big difference between these two things is that on the negative side, it goes in the opposite direction. Now let's talk about the graph of a piecewise defined function. So let's sketch the graph of f of x equals x squared if x is less than or equal to 1, and 2x plus 1 if x is greater than 1. So the way to graph a piecewise function is to get some values, or at least this is one way to graph a piecewise function. So when I'm graphing it, I'm going to graph it in pieces. So I'm going to focus on f of x equals x squared, but then I'm only allowed to plug in values of x that are less than or equal to 1. So I can plug in, for example, -3, -2, -1, 0, and 1, but I cannot plug in anything larger than 1. That's what the rule says. So when we plug in -3, -3 to the second power is positive 9, -2 to the second power is positive 4, -1 to the second power is 1, 0 to the second power is 0, and 1 to the second power is 1. Now what I can do with those, of course, is I can sketch a graph, right? So let's see here. Let's sketch this out. There's 5, 6, 7, 8, 9. So when I plug in -3, I get +9. -2 gives us +4. -1 gives us 1. 0 gives us 0. And +1 gives us +1. So the graph continues in this direction, but it stops right here at x equals 1. Now, why does it stop? Well, because for the rest of this function, when x is greater than 1, it's going to be 2x plus 1. So now we're going to graph f of x equals 2x plus 1 for values of x that are greater than 1. Now, even though it says strictly greater than 1, I still like to plug in 1 myself. So I'm just going to plug in 1, 2, 3, and 4, and then we'll talk about what to do with 1, because technically we're not allowed to plug in 1, are we? Because it says strictly greater than. But let's plug it in anyway, and then we'll talk about what to do. So when we plug in 1, we get 3, right? Just plugging 1 into here. When we plug in 2, we get 2 times 2 plus 1, that's 5. When you plug in 3, you get 7. And when you plug in 4, you get 9. So we can go ahead and continue graphing over here. So when I plug in 4, I get 9. When I plug in 3, I get 7. When I plug in 2, I get 5. And when I plug in 1, I'm getting 3. But again, that point is not really supposed to be there. So did you see what I did there? I made it an open circle. And that shows that that point there doesn't really exist on the graph because, again, we're not allowed to plug in 1. So you can see that in this graph, we have two distinct pieces of the graph. We have sort of the left piece, and then we have the right piece. And those are two clearly distinct functions, right? One is a parabola, and the other one is clearly a line. And I'll bring in a little better picture here just to show you what that would look like. Okay, so there you can see this is what our graph looks like. Next, let's graph the absolute value function. Now you might remember we already graphed this in a previous video, but I want to take a slightly different approach to graphing this function. So let's recall that the absolute value of a number x is equal to x if that number is non-negative, and it's equal to the opposite of x if x is negative. Okay, so let's first just understand this definition. So for example, if I were to ask you, what is the absolute value of -3? Most of you would probably just say, well, it's equal to 3. Now, if I ask you why, you might say, well, an absolute value just gets rid of the negative. Or you might say, an absolute value is the distance that a number is from 0, which is correct. But another way to think of it is that the absolute value of a negative number is the opposite of that negative number, right? So if I take the opposite of -3, that's how I turn it into +3. Now, if I have a positive number, say the absolute value of 5, I don't need to do this because we all know the absolute value of 5 is just 5. So if that number x is already positive, we just leave it alone. But if that number x is negative, we have to take the opposite of it to turn it into a positive number. So now what does this have to do with graphing? Well, we can think of this as a piecewise defined function. So in other words, when x is positive, we are simply graphing y equals x. And we know that y equals x is this line right here. So that is what the graph looks like for positive values. And then if x is negative, we are simply graphing y equals -x. And y equals -x looks like this. Now, one thing that we should point out is that technically when you plug 0 into here, you should have an open circle on the graph. But I want you to notice that these two pieces connect, so we don't have to worry about that in this case. So this gives us our very familiar V-shaped graph for the absolute value function. Now let's talk about a special function called the greatest integer function. And the greatest integer function is this notation that you see here. So it's these sort of special brackets that you can see here. And the definition of the greatest integer function is that the greatest integer function of x is equal to the greatest integer that is less than or equal to that number x. So for example, if I take the greatest integer of 2, that's just going to be 2, because 2 is the greatest integer that is less than or equal to 2. But if I were to plug 2.3 in there, the greatest integer, right, the largest integer that is less than 2.3 is still the number 2, isn't it? If I plug in 1.999, the greatest integer that is less than 1.999 is 1. The greatest integer that is less than 0.002 is 0, etc. For negative values, the greatest integer less than or equal to negative 3.5 is negative 4. So when you go to graph this, what happens is when you plug in a constant, so when I plug in a number like 0, the greatest integer of 0 is 0. Okay, and it's going to stay 0 until we get to the number 1, and then the greatest integer of 1 is going to be 1. But if I plug in 1.5 or 1.7 or whatever, it's going to stay 1 until we get to the number 2. And the greatest integer less than or equal to 2 is 2, and it's going to stay that way until we get to 3, right, etc. And it does the same thing in the other direction here. So what you get is something that we call a step function. Okay, and a step function is a more appropriate name for this function, but the technical name is the greatest integer function. So we just like to keep this example in mind because it is useful sometimes in the future to refer back to this special function. Now we have an example of how a step function can be useful. So this is a cost function for a global data plan. Suppose that a global data plan costs $25 a month for the first 100 megabytes of data. So if you use 100 megabytes or less, right, which would be this right here, you are going to pay $25. But then you're going to pay $20 for each additional 100 megabytes. So if you use up to 200 megabytes, you are going to pay the original $25 plus an additional $20, which would be $45. If you use another 100 megabytes, you are going to pay another $20. So notice that we have 2 times 20 there, etc. And so what happens is you get sort of a step function in terms of the bill. So again, if you use anywhere between 0 and 100 megabytes of data, your bill is going to be $25. If you use more than 100 megabytes, but less than or equal to 200 megabytes, your bill is now going to be here, and this represents $45. If you use anywhere in between 200 and 300 megabytes, your bill is going to be $65. Between 300 and 400, your bill will now be $85, etc. Okay, so basically, when you get past a certain point, it jumps up to the next value, and it stays there until you get to the next breaking point. So this is an example of how a step function can be used in the real world. Next, let's talk about the vertical line test for functions. So if you have the graph of a function, any vertical line that you draw will only hit that graph one time. So the vertical line test says a curve in the coordinate plane is the graph of a function if and only if no vertical line intersects the curve more than once. That is to say, every possible vertical line that you can think about drawing is only going to intersect the graph one time. So you can see here, that is the case. So in the second graph over here, you can see that this is not a function, right? This graph does not represent a function because if I draw a vertical line right here, I hit the graph more than once, right? I hit it twice. And in fact, that happens multiple times in this graph, okay? So the vertical line test is a quick and easy way to mentally check to see if the graph represents a function or not. So let's go ahead and use the vertical line test to see which one of these are functions and which ones are not functions. It's very clear that the first one here in part A is not a function. Also in part D, this is not a function, and it's because you can see that when you draw a vertical line, you hit the graph more than once. And by the way, that only has to happen one time. Now, in each of these cases, that happens many, many times, okay? There are many vertical lines that you can draw that hit the graph more than once, but these are not functions. Now, the other two, part B and C here, these do represent functions, right? Because every possible vertical line that you can draw here intersects the graph at the most one time. Now, what about equations? How can you tell if an equation represents the graph of a function? So let's take a look at part A here. Here we have the equation y minus x squared is equal to 2. What I like to do for these is just solve for y, right? When you're talking about equations and whether or not something is a function, we like to solve for y. So if we add x squared to both sides of this equation, we get y equals x squared plus 2. And what we need to make sure of is that when you plug in an x value, the function can only give you one y value. It cannot give you more than one y value. So think about this. If I plug in a number like, say, x equals 5, y is going to be 5 squared plus 2, which is 27. So we get a single y value. If I plug in x equals negative 3, y is going to be negative 3 squared plus 2, which is equal to 11. Again, only one y value. So we do suspect that the answer here is yes, this represents a function. And actually, if you were to graph y equals x squared plus 2, and you could do this by plugging in points, what you would notice is that the graph looks like this. And then you can think of, if I draw vertical lines, how many times does the vertical line intersect the graph? And we can see that it only intersects the graph one time. Now, how about the second equation? X squared plus y squared is equal to 4. So for this one, I want to do the same thing. I'm going to solve for y. So first, I'm going to subtract x squared from both sides, which gives us y squared equals 4 minus x squared. And then to solve for y, I have to take the square root of both sides. This is going to give us y equals plus or minus the square root of 4 minus x squared. Now, anytime y is plus or minus, you're not going to have a function. Let's think about y. Let's assume that I choose to plug in the number x equals 0. When you plug in 0, you get y equals plus or minus the square root of 4 minus 0 squared. This is plus or minus the square root of 4, which is plus or minus 2. So notice that when you plug in x equals 0, you're getting y equals 2, but you're also getting y equals negative 2. So you're getting two values of y for a single x value. This is not a function. Now, if you go to graph this equation, you might remember that the graph of x squared plus y squared equals 4 is simply a circle of radius 2. And now you can see very clearly that when you draw vertical lines, you are intersecting the graph more than once. So the answer here is no, this equation does not represent a function. And finally, we just have a little diagram here of some useful functions and their graphs. So we have the linear functions, which includes constant functions and lines. We have the power functions, x to the n, that we talked about. We have root functions. So we talked about the square root function, but you can also talk about cube root, fourth root, fifth root, etc. Notice that the graphs are a little bit different for the odd roots versus the even roots. We can talk about the reciprocal functions, so 1 divided by x to the n. We also have our absolute value function and our greatest integer function. So this serves as just a summary of some of the functions that we looked at in this section and some other important functions that we will be talking about in the future. And that concludes this video lesson.